and welcome back to Exam Ignite. Today we are starting Module 4, Part 1 of Principles of Communication System based on the VTU syllabus 2022 scheme for the 4th semester. Like always, the video is focused on the exam-oriented handwritten notes. All the topics are taken directly from the textbook, model question paper questions, and January 2025 and July 2024 VTU question papers. So this is a way where you can focus on the most expected questions for your exam and understand the complete syllabus content. So let's get started with the Module 4, Part 1. Uh, in this, we are going to start with the digital representation of the analog signals, where you will go with the why do we need the analog signals, what are those advantages, the sampling theorem, the most important one, then pulse amplitude modulation, PAM, time division multiplexing, that is TDM, pulse position modulation, PPM, the generation and detection, then quantization process, then pulse code modulation, that is PCM, in that sampling and quantization, encoding, line codes, differential encoding, regeneration, decoding, filtering, multiplexing. Mainly, you have to also read the program, that is lab program, sampling process. You have to develop a program to display the signals and its spectrum. So let's get started. Sampling and quantization. Why digital analog signals? So digital spectrums, these are very less sensitive to the noise than those of the analog system. In the digital system, it is easier to integrate different services like audio, video in the same transmission scheme. Transmission scheme can be relatively independent of the source. So voice at the 10 kbps and the computer data at 10 kbps can be sent at the same scheme. Next, digital signal circuitry can be easy to handle and repeat. Multiplexing of analog signals is difficult and it is not efficient. Analog data transmission do not have efficient, error detection is not there, and the correction technique is not there. So this you can write. Next is sampling process. The statement of sampling theorem. It's a band limited signal of a finite energy which has all frequencies lesser than the volts. It's completely described by specifying the values of the signal at the instant of time separated by 1 by 2 omega seconds. A band limited signal of a finite energy which has frequency components lesser than the uh, hertz may be completely removed from the knowledge of its samples taken as the rate of the 2 omega sample per second. You need to know sampling theory for the low pass signal. It is a band limited signal that have frequency omega hertz and can be completely described by its samples if the sampling theorem, that is sampling frequency, that is fs, is greater than or equal to twice the highest frequency of the message signal, that is fs is greater than or equal to 2 omega. The time domain analysis is analog signal is given like this, periodic impulses are there, so the discrete time signal is represented like this. Now comes the proof. Let our g of t be continuous wave signal which is sampled by the pulses. Sampled output is given as g omega is delta s of t is equal to gt of s delta of t, like that p equation 1. Periodic impulses string, that is s omega delta t, that is given in the equation 2. On substituting this in equation 1, we get this equation. After that, you need to split it. You need to take the g of t in make t as nt of s. Then where g of nts is what? Basically g of t sampled only. So 2t is equal to nts, as I said. Now next is frequency domain. Taking the Fourier transform of the equation 1 of our first equation, we get gs of t is equal to gf of g of f star s into delta of f, where s into delta of t is equal to f into sigma n is equal to minus infinity to infinity delta of f minus n fs, that is our equation 5. Now substitute the equation 5 in the equation 4. You get the next equation. So we know that by the convolution property, we know the property which is given here. So based on this property, we can write the above equation in this format and consider that as equation 6. By the shifting property here, first we will be using convolution property. Next, by the shifting property, we are going to the spectrum of the signal or original signal is given in this way. The spectrum of the sampled signal is given like this. So the above shows g of t is placed at the plus or minus fs or plus or minus 2fs or plus or minus 3fs. It means g of f is periodic in the fs. If we consider fs as 2 omega, then you get this which is in the range of minus omega less than or equal to f, which is less than or equal to omega. By the using that, for that we can write the expression where our g of f will be sigma summation of n is equal to minus infinity to infinity g of n e power minus j 2 pi fn, where our f is a frequency of discrete time signal. Replacing the g of n by the g of nts, we get for the above equation, you just replace that. So we know ts is equal to what? 1 by fs. So replace that, we get a final equation. By taking the inverse transfer function, we get the equation. Next is reconstruction of g of t. Here I of t of the above equation is taken. For that we take the frequency range of minus omega to omega. We get this, put the integration symbol, interchange the order by summation and integration. If we interchange, we get this. And then as we know, applying the limit, taking the integration of that and apply the limit, substitute, simplify, and you need to know that the sine theta is equal to 1 by j exponential of j theta minus exponential of minus j theta. Then fs, we know it is 2 omega, substitute that also. Then tf is equal to 1 by fs, that is equal to 1 by 2 omega. Substitution and cancellation, these are all easy, just substituting and cancelling. Do that, and finally you get that sine pi omega pi theta by pi theta is sine theta. So by expanding the above equation, we get the final equation as g of t. So what are the comments you can say is the sample of g of nts are weighed by the sine function. The sine function is the interpolation function. Reconstruction of g of t by the LPP, that is when interpolated signal of the above equation is passed through the low pass filter of between minus omega less than or equal to f, which is less than or equal to omega. The reconstruction wave is obtained. So pulse amplitude modulation PAM, the amplitude of the pulse is directly proportional to the amplitude of the modulating signal. You should know this equation. Main theme of the PAM. Signal at the sampling instant, keeping the width and the position constant. So how we generate? We write down the block diagram. M of message signal is given. We are having a low pass filter, multiplexer, and for that we give a pulse train generator which gives the pulses that will give us the y of t. And next the pulse shaping network it passes through, and finally we get the amp signal as S of t. The modulating signal M of t is a signal to be transmitted. It is given by the low pass filter to the band limit. The cutoff frequency of the low pass filter is equal to the highest frequency present in the M of t. So the low pass filter, it avoids the aliasing effect. So the band limited signal is then sampled at the multiplexer. Now the multiplexer samples, that is M of t, with the help of the pulse train generator which produces a train of pulse. The multiplication of that M of t and the P of t produces a PAM signal, that is our Y of t. The top of the pulses are varied according to the amplitude of the M of t. Now the pulse changing network produces a flat top pulses which is required PAM signal as shown below. So this is our M of t we will be giving. We will be giving a train of pulses P of t. Finally we get the Y of t, and this is our S of t, our PAM signal. Here let S of t denote the sequence of the flat top sample. You can observe here the flattest top. It has got flat top. So signals of the PAM, and it is expressed as what? S of t is equal to summation of n is equal to minus infinity to infinity g of nts P of t minus nts, where g of nts is the sample value of the g of t obtained at t is equal to and TS. TS is the sampling period, PT is the standard rectangular pulse train of the duration T. Then what is the advantage of PAM is it is base for all the digital modulation technique. It is main basic. Now disadvantages due to the Nyquist criteria, it requires high bandwidth for the transmission. Since the amplitude keeps varying, so there is noise associated with it. Then detection of PAM signal. Once the PAM is done, we have to get back the message signal. The original signal M of t is obtained by passing the PAM to the reconstruction filter followed by an equalizer. So PAM signal is given S of t, reconstruction filter, then equalizer, then message signal M of t. Recovered M of t from the PAM signal. Next is time division multiplexing. Time division multiplexing, it is a method of transmitting and receiving the independent signals over a common channel by the means of synchronized switches at each end of the transmission line so that each signal appears on the line only a fraction of time in altering pattern. So this is a block diagram of the TDM. We are having low pass filters through which we will send the message signal inputs. Here these are all called as an anti-aliasing filters. We are having commutators. From that it is sent to the PAM, from then communication channel, and from there PAM detector. Pulse amplitude detector. For this pulse amplitude modulator and detector, we give the clock pulses. Finally, we have a decommutator. These are all synchronized. And finally, it is again sent to low pass filters. And from there, we obtain the message signal as an output. So this is diagram. Each input signal is first band limited by the low pass filter to remove the high unwanted frequencies. Main thing is it removes high unwanted frequencies. The output of the anti-aliasing filters are then fed to the commutator, which is an electronic switching circuitry. The function is what? To take the narrow sample of each of the n samples of an input at the rate of fs is greater than or equal to 2 omega. To sequentially interleave or multiplex the n samples inside the sampling interval, that is ts is equal to 1 by fs. Now the multiplexer signal is then applied to the pulse amplitude modulator, whose purpose is what? To transform the multiplexed signal into a form that is suitable for the transmission over a common channel. Now what happens at the receiver end? The pulse amplitude demodulator, it performs the reverse operation of the PAM and the decommutator. So here it distributes the signals to the appropriate low pass reconstruction filters back, and the decommutator operates in synchronized with that commutator. Now pulse position modulation, PPM. In the pulse duration modulation, PDM, the samples of the message signal are used to vary the duration of the individual pulses. This form of modulation is also referred as pulse width modulation or pulse length modulation. In the PPM, the position of the pulse relative to its unmodulated time of occurrence is varied in accordance with the message signal. That is for the case of sinusoidal modulation. Let us consider TS to be the sample duration. Using a sample of m of nts of a message signal m of t to modulate the position of the nth pulse, we obtain the ppm signal as this. S of t is given like this, where what our kp is the sensitivity of the pulse position modulator. So this is our modulating signal, this is our pulse carrier, and our ppm wave will be like this. The illustrating of the two different forms of the time pulse time modulation. We either obtain like this or this. Next is how is it generated. So the ppm signal which is generated is given by the block diagram like this. The message signal is given to the sample and hold circuit that is sent to the adder. Along with this, we are providing a pulse generator and a sawtooth generator. It is next sent to the threshold detector. From there, it forms I of t and pulse shaping filter is formed. Finally, we get the ppm signal as S of t. The message signal M of t is first converted into a PAM signal by the means of what? Sample and hold circuit, by this first one. m of t is converted. So generating a what? Staircase wave. We get a staircase wave of u of t, which is shown in the figure B for the message signal. Shown we are giving, and finally we get second step, we get the staircase signal. U of t is what? It is added to the sawtooth wave, yielding the v of t. Here it is added by the adder and we get v of t. V of t is represented like this. This is a sawtooth wave we are getting, and we get finally the composite wave obtained by adding both of them. We get this wave. This the combined V of t is applied to what? Threshold detector that produces a very narrow pulse each time, that is V of t crosses the zero in a negative. Next is the resulting sequence of impulses I of t is shown in the figure E. That is this. The sequence of the impulses is used in the generate the ppm pulse. Next, finally, the ppm S of t is generated by using the sequence of the impulses to excite a filter whose impulse response is defined by the standard pulse, that is g of t. So how can we detect this ppm? Consider a ppm wave, that is S of t, with a uniform sampling and assume the message signal has m of t, which is strictly band limited. Now the operation of one type of ppm receiver may produce the following. Firstly, it converts the received ppm wave into the PDM wave with the same modulation. Integrate the PDM using the twice with a finite integration time, thereby computing the area under the pulse of the PDM wave. Third thing, sample the output of that integrator at the uniform rate to produce a PAM wave whose pulse amplitudes are proportional to the signal samples, that is M of NTS of the signal ppm wave S of t. Finally, demodulate the PAM wave to recover the message signal. So next is the last concept in the part 1, noise in the pulse position modulation. In ppm system, the transmitted information is contributed in the relative positions of the modulating signal. The presence of the additive noise affects the performance of such system. The output signal of this noise ratio, assuming the fully load sinusoidal, is given by what? SNR ratio, that at 0 is given by pi square bt t square by a square into a square divided by 32 nq. That is, the average noise power in the message bandwidth omega is equal to omega n naught. The channel signal is to the noise ratio is therefore given by this equation 2. So this figure will denote the amplitude spectrum of the raised cosine pulse. So TS is what? Our sampling period, BT is our bandwidth, and N naught is the power spectrum. Thus, the figure is the merit of the ppm system using a raised cosine pulse is as follows. The figure merit is given by, we have to divide both of them. Finally, on dividing, we get the figure merit formula as like this. So this was all about this module, part 1 video. I hope you understood the concepts clearly. Please go through the previous, if you have not watched the previous modules videos, please go back. The links are in the description box. Go through all the concepts which are easier to understand. And please like, share, and subscribe to the Exam Ignite so you never miss an update, especially with the important questions. Thank you for watching. See you in the next video.